Unit 6, Objective 6 is solving radical equations. And like I always do, I try to start off with some easy examples, and I worked my way up to some more difficult ones or some uglier ones. So I'm going to do the exact same thing here. For this very first problem, I'm going to just get rid of this 3 first. And that means my left-hand side now is the square root of 2x minus 3 equals 5. Now that's what we want to do. We want to isolate the radical. And that's exactly what I just did by isolating the radical. Now, the 2x minus 3 is being square rooted. When we use algebra steps to solve, we always wind up doing the opposite. So the opposite of a square root is a square. So that's what we're going to do. At this point in time, to get rid of that radical, I'm going to square both sides. Now, the square root of something, when it is squared, it just means there's now 2 of these, and I get to bring one of them out. So all that does is it gets rid of the radical, and that was exactly what we wanted that square to do. That's why we did it. Now, the right-hand side, 5 squared is 25. Add 3, 2x equals 28. And so divide both sides by 2, and x equals 14. Now, you might want to take a second to plug it back in and just make sure it works. So the way we're going to check this problem is we're going to take 3 plus the square root of 2 times 14. I'm just plugging 14 in where x was in the problem, and I'm going to put minus 3, and we're going to see if it actually equals 8 like it's supposed to. So 3 plus the square root of 2 times 14 is 28. 28 minus 3 equals 8. 28 minus 3 is 25. The square root of 25 is 5. So 3 plus 5 really does equal 8. So the problem checks out. I know my answer is right. On this example right here, it doesn't look like we have a radical in it, but we really do, because the 2/3 power can actually be thought of as being a radical of the cube root and then square it. Remember this rule right here? These are 2 equivalent terms. One's in exponential form and the other one's in radical form. So this really does have a radical in it. Well, first thing we're going to do is we're going to get rid of that 3. Now that 3 is acting as a multiplier because it's a leading coefficient. So all I have to do is divide everything by 3. And what the 3's are going to cancel over there, and I'm left with x plus 1 to the 2/3 power equals 4. Now here's where we're going to apply a new rule. In order to get rid of that 2/3 power, what I have to do is I have to multiply it by 3/2 power. Now the rule for exponents is when you raise a power to a power, you multiply. So what I really have to do here is I have to raise the left-hand side of this equation to the reciprocal, the 3/2 power. But what I do to the left, I have to do to the right. So I need to raise the right-hand side to the 3/2 power as well. Now what that's going to do is the left-hand side is now simply going to be x plus 1. Because when you take 2/3 and you multiply 3/2, the rule is when you raise a power to a power, you multiply. Well, when you multiply 2 fractions that are reciprocals of each other, you get 1 as the answer because everything reduces itself. So that's the key to this problem. When you look back up at the very beginning of the problem, you know the key is going to be, in order to get rid of that 2/3 power right there, you're going to have to re-raise to the 3/2 power. And what you do to one side, you do to the other. So over here, we need to figure out what in the world is 4 raised to the 3/2 power. So over here, over on the side, I'm going to simplify. 4 to the 3/2 power is the square root, because remember the denominator of the fraction is the index of the radical. So what I'm really doing is I'm taking the square root of 4 and I'm cubing it. And the square root of 4 is 2, and 2 cubed is 8. So if I clean up this right-hand side, 4 to the 3/2 power actually equals 8. So x plus 1 equals 8. And now it's just a little, not even an intermediate school algebra problem. It's a 6th grade algebra problem. Subtract 1, and you get x equals 7. Now, if you look at the next sample problem I've got, we kind of see the same thing. I see a 3/2 power in this equation. And I know at some point in time, I'm going to have to get rid of that 3/2 power by raising to the 5/3 power, raising to the reciprocal. But it's not time to do that yet. The first thing I'm going to do is I'm going to subtract this 1. And I've got 3 times x plus 1 to the 3/5 power equals 24. Now the next step, I'm going to get rid of that leading coefficient of 3. So I'm going to divide by 3, and what I do to one side, I have to do to the other. And now I'm going to be left with x plus 1 to the 3/5 power equals 8. And now I'm to the point where I can't do anything more unless I get rid of that 3/5 power. I can't subtract 1 yet because it's in the parentheses. So the next step is raise the left-hand side to the reciprocal, 5/3. But what you do to one side, you have to do to the other. So raise both sides to the 5/3 power. What that's going to do is it's going to clean up the left-hand side, because I've raised a power to a power, and they're reciprocals, so they're going to cancel each other. So all I'm left with is x plus 1 equals whatever 8 to the 5/3 power is. Now it's time to simplify this to see what it really is. 8 to the 5/3 power is the same thing as the cube root of 8 raised to the 5th. Well, the cube root of 8 is 2. 2 to the 5th is 32. So x plus 1 equals 32. Now subtract 1 and you get x equals 31. In this equation that I'm about ready to solve, it does have a square root in it, but the radical is not isolated. The square root x plus 7 has this minus 5 hanging around with it right now. So my very first step is isolate the radical by adding 5. Move that minus 5 over to the other side of the equation, which means my equation now reads the square root of x plus 7 equals x plus 5. And now that I have the radical isolated, now I just do what I need to do to get rid of that square root. And the way you get rid of a square root is to square it. So what I do to this side, I have to do to this side. Now the left-hand side is really nice. It's just x plus 7. Because by squaring the left-hand side, all it did was it took the square root away. Over here, we actually have a little bit of work to do. This is x plus 5 squared, so this would be the same thing as x, whatever x plus 5 times x plus 5 is. Remember, since this is a binomial term, you don't just distribute the square. Now, if you FOIL really well in your head, and we're going to say you do at this point in time, x plus 5 times x plus 5 is x squared plus 10x plus 25. You can verify that if you want by FOILing this or by matrixing it, but trust me, x plus 5 quantity squared is x squared plus 10x plus 25. Now we have a quadratic. Quadratics are very nicely solved when they equal 0. So I'm going to leave everything over here on the right. I'm going to subtract the x to move it over. And I'm going to subtract the 7 to move it over. And what I'm left with now, the left-hand side totally clears. It equals 0. And now I've got x squared plus 9x. And then this would be plus 18. And this is easily factorable. The factors of 18 that add up to 9 are x plus 6 and x plus 3. If you're wondering how that came about, and if you're used to the diamond method, all we did was we factored this by thinking of 18 up here and 9 down here. And we're wondering, what are the two numbers that multiply to give us this, but the same two numbers add to give us that? And they are 6 and 3. So that helps us get the factors. And now that we have the factors, now we can get the solutions. X equals negative 6, x equals negative 3. Because if I set each one of those factors equal to 0, that's what we would get. Now, we're not done. What we need to do is we need to plug back into the original equation to check our answers. So I'm going to go back to the original equation. The original equation was the square root of x plus 7 minus 5 equals x. And I'm going to plug in negative 6 first. The square root of negative 6 plus 7 minus 5 equals negative 6. So I'm plugging negative 6 in for x to see if this actually works out. Now, negative 6 plus 7 is 1, so that would be the square root of 1 minus 5 equals negative 6. Now the square root of 1 is 1. 1 minus 5 is negative 4. Negative 4 does not equal negative 6. So what we just found out was when we plugged in and we tested negative 6, that didn't give us a true statement. So negative 6 is out. Now let's go back to the equation again, and let's plug in negative 3. Square root, I'm going to put negative 3 right here. Negative 3 plus 7 minus 5 equals negative 3. Now, negative 3 plus 7 is 4, so that would be the square root of 4 minus 5 equals negative 3. The square root of 4 is 2. 2 minus 5 equals negative 3, which is true. Negative 3 really does equal negative 3. So when we plugged in negative 3, we got a true equation. So we get to keep -3 as an answer, but when we plugged in -6, we didn't get a true statement, and so therefore we had to throw -6 out as what we call an extraneous solution. I saved the most complicated problem for last. What happens when you have two radicals in the same equation? Well, the key is to separate them. Get one of them on one side and the other one on the other side. This would be the easiest one to attack right here, so I'm going to add square root x, add square root x. Now, that makes my equation the square root of 5x plus 4, all underneath this radical, equals 4 plus square root x. Now, the next part of the solution, the next step is going to be square both sides. So I'm going to square this side, and I'm going to square this side. The left-hand side is going to be easy. All I'm left with is 5x plus 4 after I do that. But over here on the right, we might want to take a look at what do you actually get when you square 4 plus square root x. So it would be 4 plus square root x multiplied against itself, another 4 plus square root x. So 4 times 4 is 16. 4 times root x is 4 root x. Root x times 4 is another 4 root x. And then root x times root x is simply x. So when I put all these together, I can combine these two like terms, and I get x plus 8 root x. 4 square root x plus another 4 square root x makes 8 root x, and then plus 16. Now, I took an equation that had two square roots in it, one on each side, and I wasn't able to get rid of both of them. I was only able to get rid of one of them. So now I have to do the same thing again. I need to isolate this 8 square root x. So I subtract x, I subtract x, I also subtract 16, and I subtract 16. And now I'm left with the equation with 4x minus 12 equals 8 square root x. Now at this point, I could square both sides at this point, but the numbers are going to be really big. I'm going to try to clean this up a little bit. I notice on the left-hand side, I can factor out a 4. So if I factor out a 4, I'm left with x minus 3 equals 8 square root x. Now, the next thing I can do is I can get rid of that 4 because it's a leading coefficient. I can divide both sides by 4, divide this side by 4, and divide that side by 4. And I'm left with x minus 3 on the left-hand side equals, that's an outside 8, and that's considered an outside 4, so they can reduce. So this would be 2 square root x. Now at this point, now I'm going to get rid of that square root x by squaring both sides. I'm going to square this side, and I'm going to square that side. Now the left-hand side, when 2 square root x is squared, the 2 actually does get squared, and that makes a 4. Well, the square root x gets squared also, but it's a square root x multiplied by another square root x, which is simply x. Over here on the left-hand side, x minus 3 quantity squared. This is a binomial that's being squared, so it would end up being x squared minus 6x plus 9. Now, I have another quadratic, so subtract 4x. I want this thing to equal 0. So x squared minus 10x plus 9 equals 0. The factors of positive 9 that add up to negative 10 are x minus 9 and x minus 1. And if I solve for this factor, I get x equals 9. And if I solve for this factor, I get x equals 1. And you're probably just about had it with this problem. We would want to go back and plug these two answers back into the original problem to see if it works. But take it from me, it does. Neither one of them need to be thrown out. And so those are our two answers to the problem. So let's go back and take a look at the original problem. Here's how you know it's going to be ugly. When there is a square root on both sides. When there's a square root on both sides, you basically have to do all the processes twice. Because when you square both sides, it's going to get rid of one of the square roots, but it isn't going to get rid of the other. So you have to isolate the one that's still there, and you have to square both sides again to get rid of the second one.